Hello, today we are continuing in our series on quantum mechanics concepts, continuing with the theme of photon polarization. And if you'll recall, in the last video we established a very important equation which said that if we look at the top line, that tells us what the math says, that a Hermitian operator acting on a ket vector, which is called an eigenvector, will produce the same eigenvector but multiplied by a real number, which is called an eigenvalue. And the point is that for every operator there will be at least two, in our case there were only two, but there will be at least two eigenvectors which will have associated eigenvalues. The point is the eigenvectors are different and there is an associated different eigenvalue for each eigenvector. That's the mathematics. Now underneath we've put down what that means in terms of the physics, that the Hermitian operator or the Hermitian matrix is the observable or the measurable. It's the experiment that you actually do to find something out. The eigenvector represents one of the many states of the system, and each eigenvector represents one of those states. And as I've said, there are two or more, and they are what's called orthogonal. What we mean by orthogonal is that if you are definitely in one of those states, then you are definitely not in any other. And then the eigenvalue is the result of the experiment. We set up an experiment which generated a red or a green light depending on whether the photon was vertically or horizontally polarized. And so the red and the green light, which tell you whether it's vertical or horizontal, that's essentially the result of the experiment. You can't directly measure the Hermitian operator, you cannot directly measure the eigenvector, but the eigenvalue, which is the measurable, that is the result that you get, tells you what the eigenvector was and therefore tells you what the state of the system was. Now I just said that eigenvectors were orthogonal. By that I mean that if you do the inner product of any two, AI and AK, these are both eigenvectors of the same Hermitian operator, then that will come out to 1 if I equals k, and it will come out to 0 if I does not equal k. And I can prove that for you or demonstrate it to be the case. Let's take a Hermitian operator acting on one of the eigenvectors, which we will just call A, to produce lambda, and I'll give it a subset A to show that that is the eigenvalue associated with that eigenvector multiplied by the same eigenvector. And let's assume that the same Hermitian operator acts on another eigenvector, which this one we'll call B, to produce lambda B times B, or acting on B, I should say. So this is the same operator, but these A and B are two eigenvectors of that Hermitian operator. Now I can create something which looks like this. I can take this equation here and I can write this. Now what does this mean? This just means that you take H and you operate on A, and that will give you a new ket vector. And then you take that new ket vector and you do the inner product with B. That's all that means. Well, what is that? That's simply B, that's this here, times HA, and HA is lambda A times A. But where you've got a number, that number can come outside the inner product because it's just a number, and that gives you lambda A times the inner product of B with A. Now let's do it the other way round. We're going to take this equation here and we're going to do the inner product of this with A. So now we get that A, H, B, so we've done the inner product here with A, is equal to A. Well, what is HB? HB is lambda B times B. But we can always take lambda B on the outside because it's just a number. So that equals lambda B with the inner product of A with B. And remember, the order always matters in this case. Now I'm going to take this result here and I'm going to complex conjugate both sides. Now let's just remind you that if you take AB and you complex conjugate it, you get BA. We discovered that in the first video. So that's just to remind you of something that we've already learned. So if we take this term here and complex conjugate it, essentially it just means reversing the two eigenvectors. So that becomes BHA. And that's going to be equal to lambda B. And that's a real number, so you don't have to complex conjugate that. BA. In other words, you reverse these two. And if you're wondering why I didn't complex conjugate H, which I should have done, the answer, of course, is it's a Hermitian operator, and where you've got a Hermitian operator, it equals its own complex conjugate, so I didn't need to do that. So this is just this equation here, all complex conjugated. And now you'll notice that I've got two equations with BH, let me get this right, with BHA. BHA equals lambda A BA. And here we've got BHA equals lambda B BA. So if I subtract the two, can we get them both on the screen? Yes. If I take that one minus that one, and that minus that, so I'm effectively subtracting one from the other. Obviously on this side, BHA minus BHA is going to equal 0. And on this side, I'm going to have lambda A into the inner product of B and A, lambda A into the inner product of B and A, minus lambda B into the inner product of B and A. So lambda A minus lambda B into the inner product of B A. Now, in order for that product to be equal to 0, either that term or that term has to be equal to 0. Well, we've already established that lambda A and lambda B are separate and different because they are different eigenvalues associated with different eigenvectors. So lambda A and lambda B are different. They cannot be the same. So when you subtract one from the other, you don't get 0. Consequently, it is that term there that must be 0. And if you've got the inner product of two eigenvectors that comes to 0, we showed that meant that they were orthogonal. And then we also learned in the last video of a term which looks like this. What that means is it's the inner product of x with y, and for physics purposes it means that it is a probability amplitude. If you prepare a photon with a polarization of y, what is the probability amplitude that it will go through x? And that is given by this inner product of x with y. That's the probability amplitude. If you want the probability, you have to take the square, or more accurately, you have to take xy and the conjugate, complex conjugate of xy. But we write that as the modulus of the probability amplitude squared. And I explained that you cannot prove that that is the case. It is asserted that that is the probability amplitude and that the square is the probability, and it works. It always works, so we stick with it. And then we looked at 4 states of polarization of photons. And I've just written them out to save me writing them out again. We looked at the state of a polarization that was entirely horizontal. We represented that by the eigenvector 1, 0. I didn't tell you why, but I will explain in a moment. You could write that as being 1 times the x, where x is the horizontal component, plus 0 times y, because if it's horizontal it's not vertical and y is the vertical component. And if you were to plot that on an xy diagram, this is the x-axis, this is the y-axis, then this would be entirely along the x-axis, and its length would be represented by the length of here, that's 1, and it's entirely on the x-axis. And you'll recall that that eigenvector had an eigenvalue of +1. Then we looked at the vertical polarization, which we characterized as having the eigenvector 0, 1. And that could be written as 0 along the x-axis, because there is no horizontal component, plus 1 along the vertical axis. And when you plot that on an xy plane, it's entirely along the y-axis. It has a length 1, because that's 1 there. And we found that lambda, the eigenvalue, was -1 in this case. Now let's have a look at the forward slash, 45 degrees forward slash state, which we represented by an eigenvector of 1 over root 2, 1 over root 2, which you can also put as 1 over root 2 times the x direction plus 1 over root 2 times the y direction. And that means that you've got a 1 over root 2 in the x and a 1 over root 2 in the y, and that will give you a resultant vector at 45 degrees. And by Pythagoras, the length of that vector will be 1 over root 2 squared plus 1 over root 2 squared, that's a half plus a half is 1, and you take the square root of 1 and that's 1. So again, you've got a vector of length 1 at 45 degrees to the horizontal in the forward slash direction. And then we did a fourth one, which was the backslash 45 degrees, which we represented by the eigenvector 1 over root 2 minus 1 over root 2, which you can write as 1 over root 2 of x minus 1 over root 2 of y. So if you plot that on the xy plane, you've still got 1 over root 2 in the x direction, but now minus 1 over root 2 in the y direction, which gives you a vector in the backslash direction. And its length will also be 1, because it's 1 over root 2 squared plus minus 1 over root 2 all squared is a half plus a half is 1. Take the square root and you've got 1. And for these two eigenvectors, we got, again, eigenvalues of 1 and -1. And I hope we can now see what these actual numbers that I didn't tell you what they were, I simply asserted these two and then we derived these two. You can now, I hope, begin to see what they actually represent. These numbers represent the probability amplitude of the photon being able to go through a polarizer in the x or the y direction, in the horizontal or the vertical direction. Let's just have a look. Remember, probability amplitudes have to be squared. Strictly, you have to take them with their complex conjugate, but squared if there is no complex number in order to get to the probability. So what we're saying is that if the vector is 1, 0, and 1 is x and 0 is y, which is what we've got here, then the probability amplitude of going through the x is 1, which means the probability is 1 squared, which is 1, which means the probability of a photon that is in the horizontal polarized state going through a horizontal polarizer is 100%. And the probability of it going through a vertical polarizer will be 0 squared equals 0, no chance. Here, the probability of a photon polarized in the vertical direction going through a horizontal polarizer is 0 squared, 0, and going through a vertical polarizer is 1 squared, 100%. Then we take a photon polarized in the forward slash direction. The probability of it going through a horizontal polarizer is 1 over root 2 squared, which is a half, and the probability of it going through a vertical polarizer is 1 over root 2 squared, a half. Exactly right. And then we take finally the backslash. What is the probability of it going through a horizontal polarizer? 1 over root 2 squared, a half. What is the probability of it going through a vertical polarizer? That's minus 1 over root 2 all squared, which again is a half. So these values in this vector here simply represent the probability amplitudes of a photon prepared in this state going through either the x, i.e. horizontal, or y, i.e. vertical polarizer. So now I want to use these four terms to see if we can guess what the vector will be, the eigenvector will be for a general polarizer which is at an angle theta to the x-axis. So we're now just not going to just restrict ourselves to horizontal, vertical or forward slash backslash. We now want the general solution for any angle theta. I think you can see that what we're going to end up with on the graph over here is a vector which is going to be at an angle theta to the horizontal, and it's going to be of length 1, and it's going to be made up of some probability amplitude times the x basis plus a probability amplitude times the y basis. So let's just repeat that on the xy plane, where this is x and this is y. If we've got a vector which is at an angle theta to the horizontal, that angle is theta, and it's of length 1, then the vector, which we shall represent as this, that's the eigenvector, and it's an angle theta to the horizontal, is going to be characterized by two probability amplitudes, alpha and beta. And that can be written as alpha times the x basis plus beta times the y basis. That was the pattern that we used throughout in the previous eigenvectors. So what is alpha and beta? Well, alpha will be the x coordinate and beta will be the y coordinate. If the length of the vector is 1, it's pretty easy to see that the x coordinate is just the cosine of theta. So alpha is the cosine of theta. And beta, which is essentially the y coordinate, is the sine of theta, because the length is 1, so it's just sine theta. So if I'm right, that means that you can represent the, as it were, theta eigenvector by the general term cosine theta sine theta. And let's just remind ourselves that these, therefore, we've now discovered are probability amplitudes, which you square to get probabilities. So if this is right, we could ask ourselves the question, if you prepare a photon in the theta direction, polarized in the theta direction, what is the probability of it going through an x or horizontal polarizer? Answer, cos squared theta. What is the probability of it going through a vertical polarizer? Answer, sine squared theta. And this sounds as though it might be right, because you may recall when we did the classical mechanics videos on electromagnetic radiation and looked at polarization then, we showed that if you put a photon first through a horizontal polarizer so that it's horizontally polarized, the intensity of the radiation that passes through a second polarizer that's at an angle theta will fall by cos squared theta. Now in that video what we were arguing was that the overall intensity of the radiation drops off by cosine squared theta. What we're now saying is, which of course amounts to the same thing, that the probability of any given photon prepared in the theta state going through a polarizer that is horizontally that is in the horizontal polarization direction is going to be cosine squared theta. So that amounts to the same thing. If the intensity falls off classically by cosine squared theta, that is exactly analogous to the fact that the probability of photons going through is cosine squared theta, so fewer will go through. And if fewer photons go through, then there will of course be less intensity, because each photon carries a certain amount of energy. The energy of course is represented by E equals hf, where h is Planck's constant, E is the energy, f is the frequency. So every little photon contains a quantum of energy which contributes to the intensity, and if only cosine squared theta of them get through, then the intensity will fall off by cosine squared theta. So this result here completely agrees with what we get from the classical experiments. But of course we'll need to do some tests to make sure that this works out. The first thing we need to do is to, if we take our polarizer at an angle theta, what we want to do is to find one that is orthogonal to it, that is 90 degrees to it. So there's the one this angle here is 90 degrees. And if that is 90 degrees, it's not difficult to show that that angle is also theta. So what now are the x and y coordinates of the, as it were, the reverse vector? Well, the x coordinate is going to be minus sine theta, and the y coordinate now is going to be cosine theta. So now I've got that as being my eigenvector for the orthogonal vector to the one which was at theta to the horizontal. That's that one, which just a moment ago we showed was cosine theta, or theta, and sine theta. So I assert that those two are orthogonal eigenvectors. And of course, if they are orthogonal, then we know that their inner product must be zero. So we better just check that. Is it true that these two vectors, that is, we prepare the photon in this state, which is orthogonal to this, and we ask ourselves, will it go through the polarizer, which is at an angle theta to the horizontal? And the answer we are expecting is no, and therefore that this inner product will be zero. Well, is it? Let's just see. We take this term here, which is cosine theta sine theta. So we write that, if you'll recall, as a row vector, and you take the inner product with the orthogonal eigenvector, which is minus sine theta cosine theta. And of course the rule, you remember, is you multiply that by that and you add that times that. Well, cosine theta minus sine theta is one complete, that comes a minus cosine theta sine theta. Add sine theta cosine theta. So it's a minus plus, and that's going to equal zero. So yes, it turns out to be exactly what we would have expected. We better just check, of course. Let's do a few more of our tests. The next one we're going to do is we prepare it in the theta direction and we ask, will it go through a polarizer at angle theta? Well, the answer is yes, it will, 100% certain. So the inner product of these two had better be 1. Is it? Well, let's just write it down. We've got the cosine theta sine theta, which of course, just to remind you, should be complex conjugated, but there is no complex term, so we don't need to worry. There's no imaginary term. And then we multiply that by cosine theta sine theta, and we get cosine theta times cosine theta is cosine theta squared plus sine theta times sine theta squared, cos squared plus sine squared equals 1. That works. Oh, and let's just be pedantic and check that the orthogonal versions of these, that's the orthogonal to the theta direction, if we prepare it in that state and try and put it through a polarizer in the same direction, of course it should go through 100%. Let's just test. That will be minus sine theta cosine theta minus sine theta cosine theta. And once again, you've got minus times a minus will give you a plus sine squared theta plus cos times cos, cos squared, sine squared plus cos squared equals 1. So far it all works. Let's now do this inner product. That means we prepare it at an angle theta and we ask, will it go through an X polarizer, in other words, a horizontal polarizer? Now, we've already answered that, because that, we said, is exactly what these terms tell you. These are the probability amplitudes of going through the X and the Y polarizers. So if the probability amplitudes are given here, the probabilities are the squares. So what is the probability of a photon polarized in the theta direction going through an X or horizontal polarizer? it's given by the square of this amplitude, cos squared. So we already know that, we worked it out. But this better be the same. If we prepare it in the theta and put it through an x or horizontal polarizer, we should get a probability of 1/2. Let's see if we do. So we are going to take the complex conjugate of x, well that's just 1, 0, because there are no imaginary numbers, multiplied by cosine theta, sine theta, and of course all of that, if you want the probability amplitude, sorry, if you want the probability, has got to be squared. Well, 1 times cos theta plus 0 times sine theta is just cos theta, and cos theta squared, or cos squared theta, that's exactly what we would have expected. And let's just do the final version for completeness. This inner product says if you prepare it in the theta state, will it go through the y or vertical polarizer? And if you want the probability, you've got essentially to take the square of that. So the y is 0, 1, and the theta polarizer is cosine theta, sine theta, and we've got to square that if we want the probability. And now you've got 0 times cosine theta plus 1 times sine theta, so that's just sine theta, square it, sine squared theta. So that exactly accords with what we would have expected from the probability amplitudes. Probability amplitude for going through x is cos theta, so probability is the square of that. Probability amplitude of going through the y or vertical polarizer is sine theta, so the probability is the square of that. So far, it's all working. So now let's take the most general case of all. This must be the acid test. We take unpolarized light and we put it through a polarizer in the, let's say, angle alpha to the horizontal. So it's an angle alpha to the horizontal. And we will get light polarized, of course, at that angle. Now we put that through a polarizer which is angled at the angle beta to the horizontal. This is the most general case. And we say if you prepare light in the alpha state, what is the probability of it going through the beta polarizer? Well, let's remind ourselves of the alpha state will of course be the cosine of alpha and the sine of alpha. We're just replacing theta by alpha here. And the beta state is going to be the cosine of beta and the sine of beta. So those are just the two states. And then we know that the probability of a photon prepared in the alpha state going through a beta state can be written as the inner product of you prepare in the alpha state and you want to know will it go through the beta polarizer. So that's the probability amplitude, and if you want the probability you have to square it. Okay, so let's just write that out. That will be cosine beta sine beta, that's for this one. And again I'll say you should take the complex conjugate, but there are no imaginary terms, so we don't need to worry. Multiplied by cosine alpha sine alpha. And if you multiply that out, you're going to get cosine beta times cosine alpha plus sine beta times sine alpha. So that's cosine beta cosine alpha plus sine beta sine alpha. And that term, of course, has to be squared if you want the probability. So this is all squared. Now you have to go to your table of mathematical identities. I can never remember these things, I have to look them up. I'm sure I learned how to do it once, but I don't suppose I ever can now. But you look up cos beta cos alpha plus sine beta sine alpha, and you will be told that that has an identity. It is exactly equivalent to the cosine of alpha minus beta. That's the term inside the brackets is equal to cosine of alpha minus beta. So that has to be squared to give you the probability of something prepared in the alpha state going through the beta polarizer. And essentially, if you think about it, what we were saying is this is the angle alpha, this is the angle beta, that's that complete angle there. So the angle alpha minus beta is just the angle between the two. It may have a minus sign, but let's forget that for a moment. And we can call that, we can say that the angle between the two, alpha minus beta, is theta. And so what we've now got is that the probability of the photon prepared in the alpha state going through the beta state is equal to cos squared theta, where theta is the difference between the two angles. And that makes sense. So we've now got another cos squared term for the probability. That's the probability, let's just write that out again, that if you prepare in the alpha state and try and put it through the beta polarizer, the probability is given as the inner product squared, and that comes to cosine squared theta, where theta is the difference between the angles of the two polarizers. And let's just see if that makes sense. What happens if alpha equals beta? They're the same angle. There is no difference between them. Theta will be 0. Cosine theta is 1. Cosine squared is 1. The probability of the photon going through a polarizer at the same angle is 1, of course. What happens if theta is 90? If they are orthogonal, if they are 90 degrees apart, then you expect that should be 0, and cosine of 90 is indeed 0. Cosine squared is 0. What happens if theta is 45 degrees? You would expect, of course, there to be a half probability, and cosine theta is 1 over root 2. Cosine squared theta is a half. It's working. Now you'll recall that I told you what the Hermitian operators were for the vertically polarized and horizontally polarized experiment, or the / / experiment. So now I better tell you what the Hermitian operator is for the theta and the orthogonal to theta experiment. This is for any value of theta. The Hermitian operator is going to be the cosine of 2 theta, sine of 2 theta, and sine of 2 theta minus cosine of 2 theta. I can't derive that for you, I'm just going to assert it. You will, however, see that it is Hermitian. There is no imaginary term in it, so but these two are the same, which is what they would need to be if, when you reverse them, they remain the same. Now I just need to explain a few identities. Again, I never remember these, but you can look them up and you can see that the cosine of 2 theta is 1 and the same as cosine squared theta minus sine squared theta. That's an identity. And the sine of 2 theta is equal to 2 times sine theta cosine theta. These are just mathematical identities. You can look them up. I can never remember them. I have to look them up too. Then I'm going to use a bit of shorthand here. I'm just going to put C, and that stands for cosine theta, and I'm going to put S, and that stands for sine theta, to save me writing it out quite so much. So cosine 2 theta is going to be cos squared theta minus sine squared theta. So if I rewrite this here, I'm going to have cosine squared minus sine squared using my shorthand. The top right hand corner is sine 2 theta, which is 2 sine cos. So that's going to be that. The bottom left hand corner is also going to be 2 sine cos. And the bottom right hand corner is going to be minus this term here, which is just going to be sine squared minus cos squared. So that's the shorthand version of this Hermitian operator as adjusted by the identities. And of course, what we are saying is that if you act on the theta state, which is cosine sine, you should get a real number times the same, times the same state, cosine times sine. And that looks at first sight a little horrendous. So let's take our time and work out what that amounts to. So if we multiply this by this plus this times this, we're going to get cosine cubed minus sine squared cosine. That's cosine cubed minus sine squared cosine, plus 2 sine cosine times sine, which is 2 sine squared, times just the cosine. That's the top term. The bottom term is going to be 2 sine cosine times cosine, so that's going to be 2, sine times cosine, so it's 2 sine cosine squared, plus sine cubed minus cosine squared sine. And that can be simplified into cosine cubed, which is this term here. Now if you look at this, you've got minus sine squared cosine plus 2 sine squared cosine, simply becomes plus 1 sine squared cosine. This here is a 2 sine cosine squared minus cosine squared sine, so that's just sine cosine squared plus sine cubed. Now if I take cosine out of the top, I can write that as cosine into cosine squared plus sine squared. And if I take sine out at the bottom, I've got sine into cosine squared plus sine squared. And since cosine squared plus sine squared is 1, cosine squared plus sine squared is 1, this amazingly simply reduces to cosine sine. So, I said this acting on this eigenvector will be a real number times the original eigenvector, and that's exactly what it's turned out to be. And what then is the eigenvalue? It's just plus 1, because you get the original eigenvalue without any additional numbers, so it must just be 1 times that original eigenvalue. And I guess you want me to prove that the Hermitian operator acting on the orthogonal vector to the theta 1 will also give an eigenvalue, but this time of -1. So I've written it out. This is the Hermitian operator acting now on the orthogonal version, which is minus sine cosine. If you multiply that out, you will get minus cosine squared sine plus sine cubed plus this term times this term, which will be 2 sine cosine squared. And then on the bottom, you're going to get 2 sine cosine times minus sine, so that's minus 2 sine squared cosine. And then this times this is going to give you sine squared cosine minus cosine cubed. And you can simplify that by noticing that you've got a minus cosine squared sine and a plus 2 cosine squared sine. So that just becomes a single sine cosine squared plus sine cubed. And here you've got a minus 2 sine squared cosine plus sine squared cosine, just gives you a minus sine squared cosine minus the cosine cubed. And if you take sine out at the top, you've got sine into cosine squared plus sine squared. And in the bottom, if you take the cosine out, you get cosine into minus sine squared minus cosine squared. And that, since cosine squared plus sine squared is 1, just gives you sine. And minus sine squared minus cosine squared is -1, so that gives you minus cosine. And if you multiply top and bottom by -1 and take that outside, you get minus sine and cosine, and -1 has become the eigenvalue. So we've shown that the theta eigenvector yields an eigenvalue of +1, and the orthogonal to theta yields an eigenvalue of -1. Now you'll recall that from our video on electromagnetic radiation, if the wave is travelling in the z direction, then the E field, and indeed the B field, but we're only going to think about the E field, the electric field of the electromagnetic wave, oscillates in a plane which is perpendicular to the direction of travel. And in the case of unpolarized light, those oscillations will be in all directions on that plane. They cannot have any component in the z direction, so they can't point out here at all, because they must always oscillate perpendicular to the plane. We showed that in the electromagnetic radiation. And of course, you can always resolve all of these E vectors into two vectors, one in the x direction and one in the y direction, and then the actual wave is travelling in the z direction. So we've got an EX component and an EY component of all of the E vectors in the unpolarized light. Now, it just so happens that if the EX vector and the EY vector, the resolved components, are 90 degrees out of phase, you get what's called circularly polarized light. And the conditions for that are that the wave in the EX direction will be some maximum amplitude, E0, times the sine of kz minus omega t. And the wave in the y direction will be E0, the same amplitude, times the cosine of kz minus omega t. And when that happens, the two waves are 90 degrees out of phase. What that essentially means is that when this is at a minimum, this will be at maximum, and vice versa. And so in a sense, if you plot on a chart, this is the x direction, this is the y direction, let's say, actually I've got it the wrong way around, haven't I? This is the x direction, this is the y direction. When x is at a maximum, y is at a minimum, so the vector looks like that. Then a quarter of a wavelength later, x is at a minimum, x is at a minimum, y is at a maximum. And then a quarter of a wavelength later, y is at a minimum, but x is at a maximum the other way. And then a quarter of a wavelength later, yes, you guessed it, it's there. So effectively, what it looks as though the vector has done is it's just gone round in a circle. And that is called circularly polarized light. So guess what? We're going to have to find the eigenvectors associated with circularly polarized light. So there are two directions the light can be polarized. It can be obviously polarized clockwise circularly or anti-clockwise. And if we go with what we have said in the past, then we would say that the eigenvector associated with that will be some amplitude, the probability amplitude, times the x or horizontal polarization basis vector plus some probability amplitude of the going through the y polarizer or the y basis vector. And we also learnt from the beginning of this video, remember when I drew out the vectors we'd already established, the eigenvectors we'd already established on those charts, we showed that their length was 1, which essentially meant that the probability amplitudes, when squared, must add up to 1. So alpha squared plus beta squared equals 1. If this is going to follow the pattern of what we have already learned. Well, we're a bit stuck, because if you look at it, we have already used every form of alpha beta that you could possibly want when we took cosine theta and sine theta as being the respective values of alpha and beta for a polarizer that is polarized in the theta direction. There are no more numerical options which will give us an alpha squared plus a beta squared equals 1. Or are there? What about if alpha is 1, so we just get x here, and beta is I, the square root of -1, the imaginary term which we've never yet come across? Now you might look at that, let's just put the 1 in there so that it's clear. It's 1 times the x plus I times the y. Now you might look at that and say, oh, hang on a minute, that doesn't satisfy this equation here because alpha squared is 1, beta squared is I squared, and I squared is minus 1, so you get 1 minus 1 equals 0. That doesn't work. And this is where I have to remind you, for the first time, when we glibly talk about squaring, what we really mean, when we talk about z squared, what we really mean is taking z times its complex conjugate. So if you want to square, you always have to do the number times its complex conjugate. So when you take 1 squared, that's fine, there's no imaginary term. But when you take this term, you have to multiply by its complex conjugate. What is its complex conjugate? You just change the sign of the imaginary term. So this becomes I times minus I. And I times minus I is minus I squared, and since I squared is minus 1, minus minus 1 is plus 1. So you get 1 plus 1 equals, oh dear, 2. That's no good. We're going to have to do normalization. What are we going to have to do to get that to add to 1? We're going to have to divide each of these terms by root 2. So we're actually going to get, instead of 1, we're going to get 1 over root 2 times the x plus I over root 2 times the y. Now when you do the square, you get 1 over root 2 squared is a half. When you do this, you'll get I over root 2 times minus I over root 2, its complex conjugate, which will be a half, and the half plus a half will give you 1. This is called normalization. So consequently, what we found is that the vector, the eigenvector for a circularly polarized photon is given by 1 over root 2 and I over root 2. Oh, and guess what? If the circularly polarized clockwise photon polarization is given by 1 over root 2 and I over root 2, guess what the anti-clockwise polarized state is given by? It's 1 over root 2 and minus I over root 2. And I can check that because, of course, they are orthogonal. And so what you would expect is that if you prepare in one state and try and put it through a polarizer in the other state, you won't get anywhere. So let us prepare in the anti-clockwise state and try and put it through the clockwise state. These two states should be orthogonal, are they? Well, that will be the clockwise state is 1 over root 2 and I over root 2. But remember, this is now the bra vector. You have to complex conjugate. So this now has to have a minus. And then you put it through the anti-clockwise, which is 1 over root 2 minus I over root 2. And what do you get? You get 1 over root 2 times 1 over root 2 is a half. You get minus I over root 2 times minus I over root 2, and minus times a minus gives you a plus. So it's plus I squared over 2, but I squared is minus 1. So you've got a half minus a half equals 0. Okay, now let's do an experiment. We're going to take light which is circularly polarized, and we're going to put it through a polarizer which is angled at theta, any theta. And we're going to ask ourselves, what is the probability of that circularly polarized light getting through that polarizer? Well, we've got the tools to do it. The probability, as we have said before, is simply the probability amplitude, which is you prepare in the clockwise state and you put it through the theta polarizer, and that has to be squared. And just remember, that means multiplying by its complex conjugate, should it come to that, and it probably will. So let's just think. We've got the theta state. Well, we know what that is. That's cosine theta, sine theta, and there are no imaginary numbers, so we don't have to complex conjugate that. and then here the clockwise state is 1 over root 2 and I over root 2. So we multiply that out, and what we're going to get is 1 over root 2 times cosine theta minus I over root 2 times sine theta. And the probability, of course, in each case is squared. But remember what we mean by squared. Squared means multiplying by its complex conjugate. That's going to be 1 over root 2 times cosine theta minus I over root 2 times sine theta multiplied by its complex conjugate. You just change the sign, so it's 1 over root 2 cosine theta plus I over root 2 sine theta. The plus is because you have to, when you complex conjugate, you have to change the sign of the imaginary term. Well, of course, that times that will exactly balance that times that. So that goes, and what you're left is simply now the 1 over root 2 cos theta times 1 over root 2 times theta, which is going to be a half cos squared theta. And then you've got minus I times plus I will become minus I squared, but that is just plus 1. Root 2 over root 2 is a half, so you're now going to get plus 1 half times sine squared theta. And that's just a half into cosine squared plus sine squared, but cosine squared plus sine squared is 1. So that's just a half. So what we've just shown is if you take polarized light, and it will work whichever direction you take it, clockwise or anti-clockwise, put it through a polarizer at any angle theta, the probability of that light getting through is 1/2, irrespective of what theta is. So in other words, the intensity of circularly polarized light going through a plane polarizer at any angle will fall off by a half. And finally, I better just tell you what the Hermitian operator is for this circularly polarized light. It is 0 minus I 0. That, as you can see, is Hermitian because when you transpose and complex conjugate, you get back to the same amount. And here's the test to see if we can find the eigenvalues. You take 0 minus I 0 and you act on the clockwise eigenvector, and that's going to produce, at least it jolly well better produce, the same eigenvector multiplied by an eigenvalue. Well, let's see, 0 times 1 over root 2 minus I times I over root 2 is of course going to be minus I squared, but that's just 1, so that's going to give you 1 over root 2. And here we're going to have I over root 2 plus nothing, so that's I over root 2. And that is the same as that, which means that the eigenvalue is plus 1. And if we do it on the other one, 0 minus I 0 times the anti-clockwise polarized light, that's 1 over root 2 minus I over root 2. We're going to get now 0 times 1 over root 2 plus these two, which is going to be plus I squared, which is minus 1 over root 2. We're going to get minus 1 over root 2 at the top, and at the bottom we're going to get I over root 2 because that term becomes 0, and that is not the same as this. But I can make it the same as this just by multiplying everything by minus 1, and now you've got that the eigenvalue of the anti-clockwise is minus 1. So we've used this formula which shows us the Hermitian operator acting on an eigenvector. We've got now several eigenvectors, produces the same eigenvector, and so far we've always had that the eigenvalues are either plus 1 or minus 1, which represent, as it were, on our equipment, the red and the green light. All we've done so far is photon polarization. Next time we shall look at electron spin. And now you'll notice that I've got two equations. with BH, let's get this right, with BHA. BHA equals lambda A BA, and here we've got BHA equals lambda B BA. So if I subtract the two, can we get them both on the screen? Yes. If I take that one minus that one, and that minus that, so I'm effectively subtracting one from the other. Obviously on this side, BHA minus BHA is going to equal 0. And on this side, I'm going to have lambda A into the inner product of B and A, sorry, lambda A into the inner product of B and A, minus lambda B into the inner product of B and A. So lambda A minus lambda B into the inner product of B A. Now, in order for that product to be equal to 0, either that term or that term has to be equal to 0. Well, we've already established that lambda A and lambda B are separate and different because they are different eigenvalues associated with different eigenvectors. So lambda A and lambda B are different. They cannot be the same. So when you subtract one from the other, you don't get 0. Consequently, it is that term there that must be 0. And if you've got the inner product of two eigenvectors that comes to 0, we showed that that meant that they were multiplied by the same eigenvector. And let's assume that the same Hermitian operator acts on another eigenvector, which this one we'll call B, to produce lambda B times B, or acting on B, I should say. So this is the same operator, but these A and B are two eigenvectors of that Hermitian operator. Now I can create something which looks like this. I can take this equation here and I can write this. Now what does this mean? This just means that you take H and you operate on A, and that will give you a new ket vector. And then you take that new ket vector and you do the inner product with B. That's all that means. Well, what is that? That's simply B, that's this here, times HA, and HA is lambda A times A. But where you've got a number, that number can come outside the inner product because it's just a number. And that gives you lambda A times the inner product of B with A. Now let's do it the other way round. We're going to take this equation here and we're going to do the inner product of this with A. So now we get that A, H, B. If you are definitely in one of those states, then you are definitely not in any other. And then the eigenvalue is the result of the experiment. We set up an experiment which generated a red or a green light depending on whether the photon was vertically or horizontally polarized. And so the red and the green light, which tell you whether it's vertical or horizontal, that's essentially the result of the experiment. You can't directly measure the Hermitian operator, you cannot directly measure the eigenvector, but the eigenvalue, which is the measurable, that is the result that you get, tells you what the eigenvector was and therefore tells you what the state of the system was. Now I just said that eigenvectors were orthogonal. By that I mean that if you do the inner product of any two, AI and AK, these are both eigenvectors of the same Hermitian operator, then that will come out to 1 if I equals K, and it will come out to 0 if I does not equal K. And I can prove that for you or demonstrate it to be the case. Let's take a Hermitian operator acting on one of the eigenvectors, which we will just call A, to produce lambda, and I'll give it a subset A to show that that is the eigenvalue associated with that eigenvector. So we've done the inner product here with A, is equal to A. Well, what is HB? HB is lambda B times B. But we can always take lambda B on the outside because it's just a number. So that equals lambda B with the inner product of A with B. And remember, the order always matters in this case. Now I'm going to take this result here and I'm going to complex conjugate both sides. Now let's just remind you that if you take AB and you complex conjugate it, you get BA. We discovered that in the first video. So that's just to remind you of something that we've already learned. So if we take this term here and complex conjugate it, essentially it just means reversing the two eigenvectors. So that becomes BHA. And that's going to be equal to lambda B. And that's a real number, so you don't have to complex conjugate that. BA. In other words, you reverse these two. And if you're wondering why I didn't complex conjugate H, which I should have done, the answer, of course, is it's a Hermitian operator, and where you've got a Hermitian operator, it equals its own complex conjugate, so I didn't need to do that. So this is just this equation here, all complex conjugated. Hello, today we are continuing in our series on quantum mechanics concepts, continuing with the theme of photon polarisation. And if you'll recall, in the last video, we established a very important equation which said that if we look at the top line, that tells us what the math says, that a Hermitian operator acting on a ket vector, which is called an eigenvector, will produce the same eigenvector but multiplied by a real number, which is called an eigenvalue. And the point is that for every operator there will be at least two, in our case there were only two, but there will be at least two eigenvectors which will have associated eigenvalues. The point is the eigenvectors are different and there is an associated different eigenvalue for each eigenvector. That's the mathematics. Now underneath we've put down what that means in terms of the physics, that the Hermitian operator, or the Hermitian matrix, is the observable or the measurable. It's the experiment that you actually do to find something out. The eigenvector represents one of the many states of the system, and each eigenvector represents one of those states. And as I've said, there are two or more, and they are what's called orthogonal. What we mean by orthogonal is that if